Welcome to Weber's Casino. We're going to play a game and introduce the notion of expected value here. So the game is this. You pay $5, I'll give you a six-sided die. You roll the die, you get one roll. If it comes up a prime number, then you lose. I get your $5. If it comes up as a perfect square, then you get your 5 back plus I'll pay you 2. And lastly, if you roll a perfect number, then you get your $5 back and I'll pay you $10. Okay. Question is this a game that you can win in the long run? That is, you keep playing it again and again, putting down your $5 and winning, sometimes losing, sometimes winning. What do you expect? You expect to be gaining money over time or losing money over time? So here we go. Here's how we figure this out. We need to find out what is the expected value of any one turn. Okay. And we look at it this way. We say, what are the outcomes? List all the possible outcomes. You could roll a 1, you could roll a 2, you could roll a 3, you could roll a 4, you could roll a 5, or you could roll a 6. Okay. If you roll a 1, the payout is, well, let's see. 1 is a perfect, no, is a perfect square, isn't it? 1 is a perfect square because it's 1 squared. So you're going to get a payout of $2. 2, 3, and 5 are prime numbers, and so you're going to lose $5 on those. A 4 is a perfect square, so you're going to gain $2 on that. And 6 is a perfect number. I don't know if you know what a perfect number is, but if perfect numbers, if you look at all the prime sorry, not all of the prime factors, but if you look at all the factors of 6, not including 6, they are 1, 2, and 3. Those are the factors, those are the things that divide into 6. And if you add those things up, it actually adds up to 6. So anyway, there aren't very many numbers that do that. So called perfect numbers. So in that case, I'm going to pay you $10. So there's 3 payouts of positive and 3 times where you're going to lose your $5. Okay. So when I want to know the expected payout, I want to say, what are the different payouts? And what's the probability of them happening? I could win $2. And the probability of that happening is a 2 out of 6 chance, right? So that's a 1 out of 3 chance. I also could win $10. And the probability of that happening is 1 out of 6. But I could also lose $5. And that's going to happen 3 out of 6 times. So, so minus $5. And that's going to be times a half. If I take each of my potential outcomes and multiply by the probability that they're going to happen and add them all up, I get what's called the expected value. So this is 4, 6 plus 10, 6 is 14, 6. And this is minus 15 sixths for a grand total of negative 1 sixth. It looks to me like I'm going to lose on average 1/6 of a dollar every time, which in the long run means the player loses and the house wins. Right? You may have a string of good luck and win a bunch. You may have a string of bad luck and lose a bunch. The probability is that in the long run you will lose. Okay, and you can do this with all sorts of casino games. Figure out look at the roulette table and look at all the different bets that you could make, and look at the probability of each bet. How much you're going to win, how much you're going to lose. Figure out the expected payout. It will always turn out that the casino is going to make money in the long run. I mean, that's how they stay in business. They make you think you're going to win, and you might win from time to time, but in the long haul, they win. Okay? That's the notion of expected value. You look at each of the possible outcomes and you multiply by their probability and you add them all up. Okay? We do a similar thing with multivariable situations. If you got a joint probability function here, probability density function f of x and y, right? It's a joint probability density function. Okay, then you can say, what's the expected x value? Well, the expected x value is the integral of x times that probability density function, dA, and you're going to integrate that over the whole R2, the whole xy plane. Likewise, there's the notion of the expected y value, and it's similar in that you integrate over the whole plane of y times the probability density function. Now, I'm using x bar and y bar are sort of like average x and average y. It looks like center of mass, and in fact, it is the center of mass. When we had a density function, where not probability density, with a density function, we didn't care if this was if the integral was 1 or not. And we calculated x bar by doing this integral and then dividing by the integral just of the density function, right? In this case, the probability density function, when you integrate it, is 1. So if I divide by 1 here, I'm not really changing the value. And the notion of the expected value of a random variable is the same thing as the center of mass of that region, so the x-coordinate of the center of mass. Likewise, the average y value is the y-coordinate of the center of mass. Anyway, there's that notion. There's a couple of problems in there, but the idea of the expected value is you look at all of your possible outcomes, you multiply each outcome by the probability of it happening, and you add them all up, and you get the expected value.